Hello everyone, welcome to Rapid Gyan. So guys, in this video I'm going to explain what are the refraction by spherical lenses, and also we will study the image formation by spherical lenses. So what are the spherical lenses? Spherical lenses are of two types. One is your convex lens, one is your convex lens which will look like this, and another one is your concave lens. So in my last video guys, I have explained what do you mean by refraction. I have explained the refractive index concept. I have explained the laws of refraction. So hope all of you have gone through those videos. Those who have not gone through that video, please go and watch that video. You can find the playlist of whole chapter in the description section below. Okay. So in this video what we are going to study, just we are going to see that what do you mean by refraction by spherical lenses, and also we will see the image formation by spherical lenses. Okay. So these are the two types of lens I have told you. Another one is your convex lens and another one is your concave lens. So what happened, if you guys remember, I have explained while explaining the mirror part, concave mirror and convex mirror. So I will write it over here. So this is the mirror and here it will be the lens. Okay. So mirrors are your concave mirror and convex mirror, and lenses are also the same: concave lens and convex lens. Okay. So what are the difference? So see, in the mirror part, concave mirror is something like that, where the inside part is the shining part, or you can say the part which will help in reflection. Correct? That's why they are called mirror. And this part is painted, and inside part is the reflection part. In case of convex mirror, this part is the part of reflection or the shining part, you can say, and this is the painted part. So this concave mirror, if you guys remember, I have told you this concave mirror is also called converging mirror. Why we call it converging mirror? Because it converts the light, and this is called your diverging mirror because it's divert the light. Correct? Because it's divert the light, but it's exactly opposite in case of lens. In case of lens, your convex lens will become your converging lens, your convex lens will become your converging lens, and your concave lens will become your diverging lens. This is exact opposite. So the image formation whatever you guys have seen in case of mirror, the same kind of the similar property is going to apply in case of lens, but it will be vice versa. Means whatever the property you are seeing in case of concave mirror, the same property you will see in case of convex lens, and whatever the property you are seeing in case of convex mirror, the same property you are going to see for the concave lens. So as I have told you, look here beta. So this is your, hold on, this is your convex mirror, convex lens. Correct? So what you are seeing, if the light ray is coming, this is being converted at one point. So that's why this is called convex mirror, is called your converting mirror. This is also called converging, or you can say converging. This is called, sorry, converging lens, and this is called your diverging lens, and this is exactly opposite in case of mirror. So hope it's clear guys. So what happened, I will explain you few properties. So if you guys remember the principal axis and all those things whatever I have explained during our time of when I was explaining the mirror, so same thing will be here. Suppose this is your lens, so I will draw one convex lens over here. So this is your convex lens. Okay, and I will draw one concave lens over here. So this is your concave lens. Okay, so what you will have to do, see, this will be your principal axis, one will be your principal axis like this will be your principal axis. In this case, this will be your principal axis. Correct beta? So in this case, the only difference is that in this case both the side of the mirror, whether the left hand side or the right hand side, both will have the principal focus and center of curvature. So I will say C1 F1. In this side this will be F2 and C2. Correct? The same thing will go for your, this is your convex lens, this is your beta convex lens, and this will be your concave lens. So same thing will go for concave lens also, that it will have both side, it will have your center of curvature and focus, and here also this will have your focus and center of curvature. So hope the concept is clear. We know that the focus is the length, focal length, this is called your focal length. So focal, both side the focal length will be same, and the focal length, that is f, will be half of your radius of curvature. So this is called your radius of curvature. Hope it's clear, guys. So this will implement for this will be applied for both the cases, means both for convex lens also and for concave lens also. Okay, guys. Also, one more thing, we know that there are few properties which we have studied. So in case of, if the light ray is coming parallel to the principal axis, so what happen in case of, if the light ray is coming in parallel to the principal axis, what will happen? So what will happen in case of mirror? In that case of mirror, in case of concave mirror, it what happen? It converts and passes through f. And in case of convex mirror, it diverges, but if you will extend, that will also pass through f. So in this case also it will be the same property. In this case, what will happen? If a light ray, in case of convex lens, remember, in case of convex lens, if a light ray coming parallel to the principal axis, remember this, guys, if a light ray coming parallel to your principal axis, this is, so after refraction it will pass through the focal. Just remember this. In this case also, what will happen? After, so this is both will show the refraction, but this is the converting one and this is the diverging one. So in this case it will reflect in this direction, in this case it will reflect in this direction, sorry, refract in that direction. So if you extend this, so this will actually pass through f. So this is one property which you will have to remember. Okay, so this is why I am telling this, because this is important while whenever you will go and you will draw the image formation. So this is important. So this is one case which you will have to remember, that if a light ray is parallel to your principal axis, after refraction, in case of convex lens it will pass through f, in case of concave lens it will be diverted, but if I will extend, this will pass through f. Hope it's clear, guys. The second property which I am going to, so this is the first property which you will have to, second property, that is, if a light ray is passing through f, if a light ray is passing through f, what will happen? It will go parallel to your principal axis. In both in this case, what will happen? The light ray will somewhere coming like this, means if I will extend this light ray, this will pass through f, and after refraction this will also become parallel to the principal axis. So these are the few rules which you will have to remember for image formation. There is one more case. The third case is that if a light ray is passing through the center of the lens, if the light ray is passing through the center of the lens, what will happen? It will go straight. In this case also it will be the same. If the light ray is passing through the center of the lens, it will go straight. So these are the three properties which you will have to remember. So if you look into your book, so these are the only three properties given. So one is this, if a light ray is parallel, so it will, after refraction it will pass through focus in both the cases. Here also, if it's already passing through the focus, so after refraction it will be parallel to the principal axis in both the cases. And here also, but in the third case, that if it is going passing through the center of the lens, it after refraction it will go straight. So these are the three cases which you will have to remember. Now we will go to the image formation. Okay, so if you guys remember, while I have explained you the image formation in the mirror case, so I have told you few positions. So on the same positions we are going to draw the image for lens also. The only difference is that whatever the position we have taken for concave mirror, the same positions we are going to take for the convex lens. And whatever the position we have taken for convex mirror, the same position we are going to take it for your concave lens. So I will start with the convex lens first. So in the convex lens, the position of the object, I will write it over here. The position of the object is, the first position is your infinity. See here, the first position will be your infinity. Hold on, here it's. So this is the position of the object. So the first position is your infinity. Guys, just don't get confused with 2f1. 2f1 is nothing but your c1, means center of curvature. So wherever it's written 2f1, you can also write c1. Here it's 2f2, means it's c2. So you don't have to be confused with that. Okay, so the first position is your at infinity. So how this will look like, I will just hold on, I will just draw the lens. So this is your convex lens. I will draw the principal axis. This is the principal axis. I will write it as f1. This you can write it as 2f1, or you can also write c1. Both are correct. Here it's f2, here it's c2. So if you guys remember, I have told you, if a light ray is coming from infinity, so that we will consider that that kind of light ray will always be parallel to your principal axis, correct? So in this case, if the object is at infinity, the first light ray will be parallel to the principal axis, and after refraction it will pass through f2, correct? The second light ray will also be parallel to your principal axis, and after refraction it will pass through f2. So where it's intersecting? So it's intersecting at f. So what will be the position of this? Is the object position. This is your object position. Okay, this is your beta object position. So what will be the image position in this case, beta? So I can say that my image position will be, image position is at f2, correct? This will be my image position. Whether the image so what is the size of the image? So size of the image is, you can say, highly diminished, or you can say point size or highly diminished. That's very small, correct? Highly diminished, or you can say point size, correct? What is the orientation of the image? Orientation of the image, that this will be inverted. Right now, since it's a point size, you are not able to say whether it's an inverted or erect, but if we will go forward, as soon as we start moving our object towards our lens, we will see that all the other images formed, all those images are inverted. So from that point we have derived that in this case also your image will be inverted. Okay, and whether the image is real image or virtual image, yes, it's a real image. Why it's a real image, beta? Because these two refracted rays are actually intersecting each other. So these are the properties. So if you can verify your properties over here, so you can see the position is at f2. F2 means your C2 beta. Sorry, F2 will be the F2 only. 2F2 is your C2. So, and the size of the image highly diminished, or you can say point size. This is real and inverted. So hope it's clear, guys. Now the second is beyond C1 or beyond 2F2. So I will just draw it. Come here. So let me draw the lens first. So hope it's clear, guys. Any one of you are having any doubt, please feel free to ask your doubts in the comment section, beta. I will get back to you for sure. Also, you can send me an email or you can WhatsApp me also. You can find my WhatsApp number, my email ID in the description section below. Okay. So this is your F1, this is your C1, this is will be your F2, this will be your C2. This is the center of the lens, and your image object position is beyond C1. Object position is beta. Object position is, I'll say, beyond C1. In the exam, if you write beyond C1 or 2F1, both are same thing, guys. Okay, so beyond C1, after what will happen? So now use the same property. What are those properties? That if the light ray will be, first light ray will, I will always send as parallel to the principal axis. So if a light ray is parallel to the principal axis, what will happen? After refraction it will pass through F, correct? Now send the second light ray. Second light ray I will send via F. So if the second light ray I am going to send via F, what will happen? After refraction it will become parallel to the principal axis, correct? So now if you can see over here, this is the point where my image will be placed, correct? This is the point. So looking into this, what you can see, what is the position of the image? So the position of the image is your between, I can say, between F2 and C2. Between F2 and C2 is your position of the image, correct? Now the next one is size. What is the size of the image? Size will be, like you can say, smaller than actual object. Size will be beta smaller than actual object. Correct? And now the its orientation. So orientation is your, it's inverted. You can say, see, this is the down, so it's inverted, correct? And this is your real image. Why it's real? Because both the refracted rays are actually intersecting each other. So this is your second case. Hope it's clear, guys. Now check here. This is a beyond C1, between F2 and C2, diminished means is smaller than the object, real and inverted. Hope it's clear, guys. Now let's go to the third position. What is the third position, beta? Let me draw this over here. This is your lens. And this is going to be your principal axis. I will write the values. This is your F1, this is your C1, this is your F2, and this is your C2. Your object is at C1. So what will happen if your object is at C1? The first light ray will always be parallel to your principal axis, and after refraction it will pass through your principal focus, correct? The second one I will pass through F, and after refraction it will pass through, it will become parallel to the principal axis. So this is your image. So if you can see, this is your image beta. Okay, this is your image. So what you are seeing, the object position at C, object position at C1, image position is also at C2, image position is beta at C2. If object is at C1, image will be at C2. Size is same size, means equal size, equal as of object, again real and inverted, hope it's clear guys. If any one of you having any doubt guys, I'm again saying please feel free to ask your doubts in the comment section. Okay, so if you can verify your third one, see the third one is that if it's at C, at C1, 2F1 is what? C1. So if it's at C1, the position will be at C2. It's of the same size, real and inverted. Now let's go to the next one. Let me draw that quickly. So here it's your lens, and I will draw the principal axis. This is your principal axis. I will just write, this is your F1, this is your C1, this is your F2, this is your C2. Object position will be between C1 and F1. Object position is between C1 and F1. So what will be the, so first light ray will be parallel to the principal axis. After refraction it will pass through F2. Second light ray I will send via F2 only. So it will come somewhere here if you actually draw. So this will be somewhere here, and after refraction it will go like this. So what you are seeing here beta, we are seeing that this is where your image will be drawn. So what is the position of the image? Position of the image is beyond C2. Position of the image is beyond C2, or you can say 2 of F2. Correct? Size is enlarged, or you can say larger than, size is enlarged, or you can say larger than the actual object size. And it's real and inverted. Real and inverted. So these are the characteristics of the images. It will, the position is beyond C2, it will be enlarged, real and inverted when your object position is between C1 and F1. If your object is between C1 and F1, this how the image will be drawn. We can verify our answer over here. Say beta, between F1 and C1, beyond C2, enlarged, real and inverted. Okay, now come to the fifth one. Hold on, let me draw that over here. Okay, so let's come to the fifth one. So this is your lens, convex lens. I will draw the principal axis. This is your principal axis. Let me write the positions. This is your F1, this is your C1, this is your F2, this is your C2, and now your object is at F1. Your object is, your object position is beta, object position is equal to F1. So what will happen? Again the same thing beta. First the light ray will be parallel to the principal axis. After refraction it will pass like this. In the second case I can say I will send the light via this. So after refraction, so this will go something like this. Okay, so what you are seeing over here beta, these two lines are, these two refracted rays are parallel lines. They are parallel lines. So what is the case of parallel lines? We know that parallel lines intersect each other at infinity. So image position will be beta, image position will be your at, I will say at infinity. This will be your image position. Okay, again this will be highly enlarged. What will the size of the object image? This will be highly enlarged beta. Okay, highly enlarged, and the other characteristics are, they will be real and inverted. They will be real and inverted. Okay, so if you come over here to verify your answer, see here, when it's at F1, at infinity, highly enlarged, real and inverted. Hope it's clear guys. Now let's come to the last position. Last position is between your lens and focal, between your lens and focal point. Hold on, let me draw the lens first. So this is your convex lens, and I will draw the principal axis over here. Hold on. So this is your principal axis, this is your F1, C1, F2, C2. What will happen beta? Now your object is over here. So if it's parallel to the principal, the first ray, always remember, first ray you will have to send parallel to the principal axis. After refraction it will pass through f2. Second I will pass beta, second I will pass through this. So this will, so what you are seeing beta, ki on the right hand side these two lines are going away from each other, correct? On the right hand side these two lines are going away from each other, so of course they are not going to meet anywhere here. So means if I will extend these, if I will extend these rays somewhere on the back side, so they are going to meet somewhere in the back and your image will be formed over here. So right now here your object position is between f1 and optical center of the, between f1 and optical center of the lens. What is your image position? Image position is beyond the object, or beyond, you can say behind the object or beyond the object. Okay, so it's beyond object. Okay, what is size? Size I can say it's enlarged. Size I can see it's enlarged, means it's a larger size than the object. So whether this image is okay, first one, it's inverted or erect. Yes, I can say this one is erect, very clear I can say. Now whether it's a real or imaginary, this one is your imaginary beta, not real. Why not real? Because the refracted rays are not actually intersecting each other, they are not actually intersecting each other. That's why we can say we are just imagining, like we are doing our imagination, that if we will extend these two refracted rays, if we will extend these two in the refracted rays on the back hand side, so at some point they are going to meet, so that we are imagining. So that's why you can say that's an imaginary image. Okay beta, so these are the characteristics. If you see over here, so see, if its object position is this on the same side of the lens, you can say okay, behind, I have told you that behind the object, this also you can say on the same side of the lens, this is enlarged, virtual and erect. So hope guys convex lens is clear. So this is the property of your convex lens. Okay, this is the property of your convex lens. Now I will go to your concave lens. Okay, okay, let me draw the lens over here. Hold on. So this is, so in case of beta convex, in case of concave lens there are only two positions. If you guys remember, in case of convex mirror also there are only two positions. So in case of convex lens, in case of concave lens also there will be only two positions. So what are those two positions beta? One position is at infinity, one position is at infinity, and another position is between optical center and the lens. So these are only two positions which we are going to study. So I will just show you the infinity. So what will happen in case of infinity beta? So now they are saying that your object position, I will write over here that object position is at infinity. So what will happen? If a light ray is coming from infinity, that light ray will be always be the parallel to the principal axis. Okay. So after refraction, this is your f2, this is your c2, this is your f1, and this is your c1. So after refraction, what will happen? So after refraction beta, this is going to be like this way. So means if I will extend this, this is going to meet some at f. This is going to meet at f. Just remember this. Okay. Now the second light ray will also be parallel to your principal axis. Correct. Second light ray will also be parallel to your principal axis. So this will also refract. And after refraction, this will also pass through your focus point f. Okay, just remember that. So in both the cases, they are going to, where they are going to intersect at f1. They are going to intersect at f1. So what is the image position beta? So image position, you can say it's at f1. Okay. Now size of the image. So size of the image, you can see that both the refracted rays are actually, not actually, means we are assuming, so in our assumption, in our imagination, they are intersecting at principal axis. So if they are intersecting at principal axis, means the image size is highly diminished. It's highly diminished or very small, highly diminished or very small, you can say. Okay. Now are they real or virtual? They are virtual. Why they are virtual beta? Because they are not actually intersecting each other. So they are virtual image, or you can say imaginary image, virtual image or imaginary image. Okay. And also the another one is your beta what's the, it's whether it will be erect or inverted. So this will be beta erect. Now again, if you ask, since it's a point size, how you can say this is erect? So because why we are saying this is erect, because in the next case what we will see, as soon as we move the object closer to the lens, we will see that this is the erect. So from that we have derived that this image will be your erect image. Okay, now I will go and I will show you the next case. Next case is that when your object is between your lens, means between the optical center of your lens and infinity. So now this will be your principal axis, I will say. Okay, hold on. This is your f1, this is your c1, this is your f2, and this is your c2, and object is anywhere, somewhere here, I will say. Object is here. Okay, so what will happen? So first light ray will always be parallel to the principal axis. After refraction it will pass through f. After refraction it will pass through f, means not actually pass through f, we can imagine that this will pass through f. Okay, and the second I will send it to the f. So this is your f, correct? This is your f. So second I will just try to send it like this. So this is the case. So after reflection this will be parallel to your principal axis. So if I will extend it on the back side, so this will intersect somewhere here, correct? This is going to intersect with us somewhere here. So this is your image position. This is going to always remember, but a refracted ray should be intersected, not the incident ray. So in this case, this one is your incident ray, but this one is your refracted ray, imagination of your refracted ray. Okay, so when your object position, in this case what is your object position? Object position was between your optical center, this is the optical center of the lens, and infinity. And image position, I can say image position is between your f1 and optical center. This is, you can say, smaller in size, smaller, I can write beta, smaller in size. This is real or virtual? This one is your virtual beta. Why it's virtual? Because the refracted rays are not actually intersecting each other. And this one is erect, you can say this image is erect. So these are the characteristic in this case. Check here beta. So if it's at infinity, these are the cases: highly diminished, point size, virtual or erect image. This is diminished, again virtual and erect, and between f1 and o. So these are the characteristics, guys. So what are the characteristics? There are 8 characteristics which we have studied. I will just quickly remind you. So the first case, when the object is at infinity. So these are the cases. The second we have studied, when your object is beyond c1 and 2f1. Third case, when we have studied, when the object is at c1. Fourth case, when between c1 and f1. Fifth case, when it's at f. Sixth case, when it's between f1 and o. So in this case we can see beyond the object, enlarged, erect, imaginary image, or you can say virtual image. Both are fine. Imaginary image, or you can say beta virtual image. And these are the 2 cases of your concave lens. These are the 2 cases of your concave lens. So let me see if there is anything else in your book on this topic. So that's it, guys. So you can see these are the 2 cases of concave lens. So guys, that's it from this video. In the next video I will start with the sign convention. We will study the lens formula and magnification, and we will solve numericals on this lens formula and magnification. So guys, those who are watching this video, those who are here at my platform first time, please subscribe the channel, please like it, please share it with your friends, and you can also ask your doubts, ask your suggestion in your comment section. You can also say how you like this video in the comment section. Thank you.